Earlier, we defined the response of a linear time-invariant system in two parts: transient response and steady-state response. We discussed the transient response in previous lectures. Now in this video, we review the steady-state response. Linear systems can be classified according to their ability to follow different possible inputs by their types. Type in this sense is determined by the number of poles at the origin. Let us consider a transfer function with the denominator and numerator polynomials factorized in first-order terms so that the constant terms of the factors are 1. In this form, the type of a system will be the power of the s term in the denominator, namely capital N. So a system is called type 0, type 1, type 2 if n equals 0 or 1 or 2, etc. For example, 1 over s plus 1 is a transfer function of first order and it is of type 0, since it does not have any poles at the origin. On the other hand, this transfer function is type 1 because of the s factor in the denominator. Note that the type of a system is totally different than the order of it. As we shall see in a few minutes, increasing the type improves the accuracy of the response. But since it also increases the number of poles at the origin, it may push the systems towards instability. To analyze steady-state errors, we shall consider a unity feedback system. So the closed-loop transfer function will be g of s over 1 plus g of s. Since the error signal E is r minus c, the transfer function E of s over r of s can be written as 1 divided by 1 plus g of s. This transfer function is also known as the sensitivity function related to g of s, and E of s can be obtained by multiplying it with r of s. To find the steady-state error for some specified reference input, we can use the final value theorem, which states the limit as t goes to infinity of E of t is the limit as s goes to 0 of s times E of s. And that means the limit of s r of s divided by 1 plus g of s. Let us start with the steady-state error to the unit step input. Since in this case r of s is 1 over s, the steady-state error will be the limit of s times 1 over s divided by 1 plus g of s. Cancelling the s variables and evaluating the limit, we get 1 over 1 plus g of 0. At this point, to simplify the notation even further, let us define the static position error constant, that is Kp, as the limit as s goes to 0 of g of s. In other words, g of 0. So the steady-state error becomes 1 over 1 plus Kp. If the system is of type 0 and the transfer function is factorized so as the constant terms of the first order factors in both the numerator and the denominator are 1, all these first order factors will approach to 1 as s tends to 0. That means Kp will be obtained as K, that is the DC gain of the system. However, for systems of type 1 or higher, it will be infinity because of the s factors in the denominator of the transfer function. Therefore, the steady-state error will be 1 over 1 plus Kp for a type 0 system, and it will be 0 for a type 1 system or a system of higher type. Next, consider the steady-state response for a unit ramp input. This time, r of s is 1 over s square. Applying the final value theorem and substituting r of s, we can cancel a factor of s in the numerator and the denominator. Still, there is an extra s in the denominator this time, so E sub ss will be 1 over limit of s times g of s. Let us now define the limit of s times g of s as kv, which we are going to call as the static velocity error constant. So the steady state error can be given as 1 over kv. Proceeding similar to the unit step input case, we see that the velocity error constant is determined directly by the type of the system. That is the number of integrators in the feed-forward transfer function. For type 0 systems, the velocity error constant will be 0. For type 1 systems, it will evaluate to k, that is g of 0. Further, for systems whose type is equal to or higher than 2, the result will be infinity. Therefore, the steady-state errors will be infinity for type 0 systems, 1 over k for type 1 systems, and 0 for systems of type 2 or higher. Since the errors with respect to a certain input and the corresponding error constants are inversely related, the error constants show the ability of the system to follow an input. We see that the error constants increase and the errors decrease with increasing system type. That means the higher the type of a system, the more accurately it can follow the reference inputs. It is also interesting to note that the static error constants are named as if implying servo systems with position outputs. Namely, if the output is position, a unit step input would be a command to the system to change its position to a new constant, whereas a ramp input would be applied if the system is to be run under constant velocity. Nevertheless, the use of error constants are by no means limited to position control systems. They are used for any physical quantity of output. So it is not surprising that we continue our analysis with static acceleration error constant. This time the reference input is a unit parabola. Therefore, R of s is 1 over s cubed. We employ the same formula for the steady state error, which can be simplified as limit as s goes to 0 of 1 over s squared g of s. We denote the static acceleration error constant by Ka and define it as the limit of s squared times g of s as s tends to 0, so that E sub ss equals 1 over Ka. For a type 0 system, the acceleration error constant will be 0, and so will it be also for type 1 systems. It takes a type 2 system, that is a transfer function that has 2 poles at the origin for a non-zero acceleration error constant. And the error constant becomes infinite whenever the type is 3 or larger. Therefore, the steady state error in the response to a unit parabola input is infinity in type 0 or type 1 systems. It is 1 divided by k for type 2 systems and 0 for higher types. As expected, systems of higher types possess larger error acceleration constants and therefore can follow the input more accurately. We can summarize all these results in 2 tables. The first one tabulates the static error constants. As mentioned earlier, a given error constant improves with increasing system type. That is, as you go the table downwards. Correspondingly, for a fixed type, the constant corresponding to a more complex input is decreasing. That is, you have smaller error constants as you move towards right in the table. In short, we have a table which has k in all diagonal locations, 0 in superdiagonal, and infinity in subdiagonal. Note that it can be expanded in this form as much as you like downwards to add higher types and towards right to add other error constants. Here is the corresponding table displaying the steady state errors for different types versus reference inputs. Its elements are simply the inverses of those in the table of error constants, except the error to unit step for a type 0 system, which is 1 over 1 plus k, rather than the inverse of k. Of course, the diagonal formation of this table can also be extended so as to include higher types or more complex polynomial inputs. Lastly, let us compare the open loop and closed loop control strategies from a steady-state point of view. On the left, we have an open loop controller which is controlling a first-order system with a time constant capital T and gain capital K. On the right, the same system is under a feedback control. Both controllers are simple amplifiers of gains Kc and Kp respectively. First, we derive the steady-state error for the open loop controller. Let us choose the controller gain as the inverse of the planned gain, that is 1 over k. This will give a unity gain from the reference input to the output, denoting the overall transfer function with GO. The error in the Laplace domain, that is R of s minus C of s, can be written as 1 minus GO multiplied by R of s. Then, for a unit step input, the steady-state error can be obtained using the final value theorem, and it turns out to be 1 minus GO of 0. Here, we see that choosing the controller gain as the inverse of the gain of the plant, we can make GO of 0 equal to 1 and therefore achieve 0 steady-state error. What about the closed loop operation? Writing the error E of s as the sensitivity function multiplied by the reference input, the steady-state error to the unit step input can again be obtained using the final value theorem, which yields 1 over 1 plus g of 0, or equivalently 1 over 1 plus kp times k. That means in closed loop operation, zero error cannot be achieved. This result is in accordance with the fact that proportional control action must result in non-zero error. It is true that at the expense of increasing kp, you can make the error as small as you wish, yet an ideal cancellation of the error is not possible. Well, does this mean that the closed loop operation should not be favored against open loop? Before making our minds up, let us consider another and more realistic scenario. Assume that the transfer function of the plant is not exactly as it is shown in the block diagrams, but that we have an uncertainty or deviation from the nominal value of k, which we can call delta k. To be able to do a comparison in numbers, let k be 10 and delta k be 1. That means the uncertainty of k is about 10%. We also assume a gain of 10 for the closed loop controller. The steady-state error in the open loop case, that is 1 minus GO of 0, will turn out to be 0.1 in magnitude. However, on the closed loop side, replacing k with its perturbed value, that is using 11 instead of 10, one obtains the error as 0.009, which is less than 1/10 of that of the error corresponding to the open loop controller. That means the open loop controller may look like resulting in zero error ideally, but in real life, where you would almost never expect nominal values, the closed loop operation is much more robust against the changes or uncertainties in the plant. This is the end of our discussion of steady-state errors in unity feedback systems. Do not forget to study the example problems and questions in your textbook and check that you can determine the type of a system, that you can determine the static error constants of linear time invariant systems, that you have an understanding of how the static error constants and the steady-state errors are related to the type of the system, have an understanding of the advantages of feedback control from the point of view of steady-state performance in LTI systems.